All right, let's open a new case file. Today, we are diving deep into the synthesis of a common chemical to solve the mystery of the missing product. Yeah, this is a classic story of expectation versus reality all playing out right inside a chemistry lab.
So our target is this stuff, ethyl ethanoate. You definitely know the smell. It's that sweet scent of pear drops, and it's a key ingredient in things like nail polish remover. We've got our reactants, ethanoic acid, and ethanol. The procedure seems simple enough, but there's always a catch, isn't there? There's a fundamental problem that haunts just about every chemical reaction.
And that leads us to the central question of our whole investigation. Why is it that in the real world of chemistry, you never get that perfect 100% of the product you were supposed to make? Where does the rest of it go? To find out, we have to start with our first piece of evidence, the blueprint for the whole operation, the chemical equation itself. Here it is. On the left, our starting materials, ethanoic acid and ethanol. On the right, what we hope to get, our ethyl ethanoate, plus a little water. But look closer. See that arrow in the middle? That double arrow is our first major clue. It means the reaction is reversible, so it can go forwards and backwards. It never fully commits to finishing, which makes it a primary suspect for our missing product. Now, before we can call this a success or a failure, we need to know what we're even measuring. We have to define the metrics that separate the perfect world of theory from messy reality. On one side, you have the theoretical yield. This is the dream, okay? It's the absolute maximum amount of product you could possibly get if every single molecule reacted perfectly. Then, on the other side, you have the actual yield. This is the cold, hard evidence, the real, measurable amount of stuff we actually managed to collect in our flask. So how do we measure the gap between that dream and the reality? Well, we use a metric called percentage yield. It's really just a simple comparison of what you actually got versus what you could have gotten. This number is going to be the final verdict on how successful this experiment really was. Okay, let's get into it. This is where we follow the numbers. We're going to break down the calculation into clear, simple steps to crack this case and find our percentage yield. So our investigation is going to follow a three-step process. First, we establish the facts by measuring our actual yield. Second, we use our blueprint, that chemical equation, to calculate the theoretical yield. And finally, we bring it all together to deliver the verdict. Phase 1 is the easy part. We just take the mass of the flask with our final product in it and then subtract the mass of the empty flask. The difference is our hard evidence, our actual yield. And in this case, it's 15.70 grams. Simple.
All right, now for phase 2, calculating what we should have gotten. We start with our main reactant, ethanoic acid. Think of it like a recipe. By adding up the atomic masses of all its parts, 2 carbons, 4 hydrogens, 2 oxygens, we get its relative formula mass, or RFM, which is 60. This number is basically a conversion key that lets us translate the mass we used into a universal unit chemists call moles, which is just a convenient way to count huge numbers of molecules. Now, check this out. In a perfect world, our chemical blueprint shows a really simple one-to-one relationship. For every 1 mole of ethoic acid we put in, we're supposed to get exactly 1 mole of ethyl ethanoate out. A perfect trade. So, if we know the ideal number of moles we should end up with, how do we turn that back into a mass we can compare? Easy. We just run the process in reverse. We calculate the RFM of our product, which turns out to be 88, and we multiply it by that number of moles. That gives us our theoretical mass, the number we've been chasing this whole time. But hold on. A quick warning from the case file. Here's a classic trap people fall into. They assume that equal volumes mean equal amounts of stuff. Nope. 25 milliliters of ethanol is not the same amount of substance as 25 milliliters of ethanoic acid because they have different densities. So the golden rule is always use mass for these calculations. Don't fall into the volume trap. All right. Phase 3, the verdict. Here it is, the formula that brings everything together. We take our actual mass from phase 1, divide it by the theoretical mass we calculated in phase 2, and multiply the whole thing by 100 to get our percentage. That's it. Let's walk through the whole case study. Say we started with 30 grams of acid. Our calculations tell us that this should ideally make 44 grams of the ester, but in reality, we only collected 18 grams. So we plug those numbers into our formula, and we get a final yield of, wow, just 40.9%. The verdict is in, and it's not great. So now the real mystery begins. Where did the other 59.1% go? Now that we have our result, the investigation takes a turn. It's time to identify the culprits responsible for all that missing product. It's time to round up the usual suspects. And here they are, our lineup. First up, reversibility. Our prime suspect right from the start, the reaction just didn't want to finish. Then we've got transfer loss. Every time you pour something, a little gets left behind. Volatility, yep, some of our product literally just evaporated into thin air. Solubility, a chunk of it dissolved in the wastewater and got washed away. And finally, impurities. What we collected wasn't even 100% pure product to begin with. And listen, this isn't just a challenge for a student in a lab. These exact same problems, these same suspects, they exist on a massive scale when companies try to manufacture chemicals for all the products we use every day. This table really highlights the difference in scale, right? In the lab, we're doing a tiny batch process with some simple glassware. But in industry, they're running a massive continuous flow through these incredibly complex distillation columns to get every last drop. They use smarter, solid catalysts to cut down on waste, and they have these sophisticated recovery systems to capture and recycle everything. It's all about maximizing that percentage yield, because for them, every lost percentage point is money going right down the drain.
So, knowing all this, how could we have improved our own result? Well, we could have used an excess of one reactant to kind of force the reaction forward. Or we could have been way more careful with our transfers and used better distillation techniques. Every little improvement really adds up. And with that, this case is closed. Let's just review the findings. We confirmed how to calculate actual and theoretical yields. We pinned down the key RFM values. But I think, most importantly, we've accepted that 100% yield is pretty much a fantasy. The real goal, the true measure of success in synthesis, is efficiency. And this formula is so much more than just math. It's really the heart of chemical synthesis. It represents that constant struggle to close the gap between what's perfect on paper and what's actually possible in the real world. In the end, calculating a percentage yield isn't just about getting a number right. It's about understanding the story of your reaction. Because a great story, much like great science,